Ja, wenn du mir auch dann die Slides im Anschluss bei Gelegenheit zukommen lässt, ja. Also, so wie es dir halt ausgeht. Ich gebe das dann weiter an die Teilnehmer.
Passt.
Habt ihr Solaranlage und Windräder daheim?
Nein, daheim nicht. Also wir haben eine ZAMG Solaranlagen oben am Dach bei uns im Kreilhaus und an der neuen Fassade. Also sie haben bei uns eine Lücke geschlossen und haben an der Fassade, bei dem neuen Teil, haben sie von oben bis unten wirklich komplett mit Solarpanelen voll gemacht. Und was ich gesehen habe, sind am Dach jetzt auch wieder neue dazugekommen. Und die eine Seite, die nach Osten schaut von dem Gebäude, ist auch schon relativ lange mit einigen bestückt. Und daheim, also dort, wo ich aufgewachsen bin, ist eines von diesen Nebengebäuden, hat seit ich denken kann, eigentlich haben die Solarpaneele am Dach oben. Also das wird eines der ersten sein. Aber sonst Solar, Wind haben wir nichts, auch am Semmering nicht, weil es am Semmering so lange mit dem Wald von den Liechtensteiner, das direkt hinter unserem Grundstück ist, so zu war. Also wir haben weder Satellitenanlage noch sonst irgendwas draußen, weil wir nicht durchgekommen wären. Und darum haben wir auch keine Solaranlage am Semmering. Und beim Schnee draußen, man muss rausfahren, muss Schnee runterschaufeln vom Dach. Ja. Und ist halt doch ein steiles Dach, also muss nicht sein.
Okay. Okay, so welcome everybody to the next lecture within our seasonal school IEEE Signal Processing Society Seasonal School on Networked Federated Learning. And one main application domain for this distributed and collaborative learning algorithms might be meteorology, and in particular the high precision forecast of sunshine and of wind. And we have the great pleasure to hear firsthand from a meteorology expert today about machine learning techniques in this field. So we will have Dr. Irene Schicker, who studied meteorology in Vienna and Innsbruck with a focus on remote sensing and glaciology. In her doctoral studies and research at the University of Applied Life Sciences, or BOKU, in Vienna, her main research topics were high-resolution numerical modeling, land use influences in high-resolution modeling, boundary layer, and mountain meteorology. Furthermore, she performed research in moisture transportation in the atmosphere, as well as climate change and renewables. In her current position at the Austrian Meteorological Service ZAMG, she is focusing on post-processing and forecasting using machine learning and data mining techniques for different temporal horizons, ranging from nowcasting to sub-seasonal time periods. And in this work, she combines heterogeneous data sources, including Internet of Things and PWS data. The main field of application in her research is renewable energy. However, also other applications such extreme event predictions like hurricanes belong to her field of expertise. Besides her work, she's an avid mountaineer, enjoying ski touring, climbing and hiking, backpacking with family and friends, using her forecasting knowledge to find the best spots for powdery slopes and enjoyable climbing conditions. Yeah, we are very happy to have you, Irene. Please take it away.
Yeah, thank you for the introduction, Alex. Yeah, so as you've heard in the introductory words, I was working quite a lot on different things, studying different things, but in the past approximately 5 to 6 years, I was mainly working in post-processing, and specifically post-processing with machine learning applications. And machine learning applications are gaining more and more attention in meteorology. So it's not like unknown field of science, but we're really using it for quite a long time. But in the past 2 to 3 years, it really increased in usage. So today I'm going to give you a short introduction on weather forecasting and also what we are using, what are the classical methods, and where we could use federated learning. So typically a numerical weather prediction or weather forecasting is done using global weather forecast models and regional weather forecast models. And global weather forecast models are built in a way that they represent the Earth with little boxes covering roughly 9 × 9 kilometers right now with the best global model. And in these boxes, they calculate the vertical exchange between the vertical levels, which go up to 50 hectopascal, sometimes even higher. And they also calculate the exchange between the horizontal boxes. So you have the vertical and the horizontal calculation. And this is done for quite a number of parameters with a time step. And this is not to be confused with the temporal frequency of forecast, which is hourly typically, but the time step is sub-hourly to calculate every 5 to 10 minutes with the global model the state of the atmosphere. And at the full hour, the state of the atmosphere is written to a file, typically. Sometimes you save the steps in between as well. And depending on the horizontal and vertical resolution, this time step varies. So sometimes it's 5 to 10 minutes, but if you increase the resolution, the horizontal resolution, the time step goes to below the minute scale. And also this time step is one of the big points in numerical modeling. If it's too small, the numerical model gets unstable and crashes. So it's a parameter which has to be chosen with some care. And what we do is we take the output or forecast of a global model and use it in our regional models, which have a resolution of, let's say, 2.5 kilometers to 1 kilometer for the rapid update cycle models, which means for Austria, we have a domain covering only Central Europe. And within this domain, we are able to increase the horizontal resolution. Otherwise, it would be computationally too costly to perform weather forecasts. So these are the basics. But a weather forecasting model needs data. So we have tons of observations, which are fed into a numerical model using data assimilation techniques like Kalman filtering or 4D VAR. And as observations right now, we have satellite data, we have observation sites, that classical meteorological ones, we have buoys, we have ship measurements, we also use radar data and data of airplanes. So airplanes have the advantage that they travel through different vertical layers of the atmosphere, and they transmit the state of the atmosphere to an antenna. And what we also have are radio sounds, which sometimes are able to go up into the stratosphere. And so we have tons of observations with different kinds of resolutions, so different kinds of temporal resolutions, different kinds of spatial resolutions. Some are only a point, some like satellite data come on a grid of 1 kilometer or 50 meters. It really depends on the type of data you have. What also is used in numerical weather forecasting, you have to have knowledge on the state of the surface layers. So you can simulate the atmosphere, this is not a problem, but then you have no idea what the soil moisture is, for instance, what the exchange of moisture fluxes between the surface and the atmosphere is. And this exchange is modeled using a surface model. And the same happens with the ocean. So it's also coupled to an ocean model. What is also fed into a numerical model or used are static grids like the topography, the land use, because depending on the land use, your surface atmospheric changes. And then you have semi-static fields like vegetation, fraction, type of vegetation, which varies on a monthly base. And what the numerical model does is calculating for every box the weather forecasting equations. And below I have an example of a very, let's call it primitive weather forecasting models and the governing equations, which calculate for every time step the state of the respective parameter. But we also have processes which are smaller than the 9 times 9 kilometers, for instance. With 9 times 9 kilometers, you most likely won't see a very small valley. So you don't know how the wind behaves in this valley. You don't know the temperature, or you don't see the temperature and the moisture exchange. What you also don't see is the onset of a convective cloud, like a thunderstorm, because this really happens on a tiny, tiny scale. So we use subgrid scale processes using parameterizations. So another source of uncertainty, because parameterizations are typically defined, or the constants in these equations are defined by field experiments. And field experiments are not performed on a regular basis, like every year we go to the Inn Valley or we go to somewhere in the Rocky Mountains, but it's done every, well, I don't know, let's say twice a decade or so. And often it's only done for one part of the world. So sometimes you use equations with constants that were derived in the Rocky Mountains and you apply them to Austria or the Alps, which means they were derived in an alpine range which goes from north to south, and you use it in a range which goes from east to west. So it doesn't really apply. And I just found this week, unfortunately it's in Dutch, but maybe it does help as well. I just found this nice PDF summarizing what a numerical weather model and climate model does. And so maybe if you're interested, you could have a look into this PDF as well. And what we can see here is for the ECMWF, the 9 times 9 kilometer would be a grid cell like this. And if you zoom into it, you would have one such a grid cell covering quite a huge part of the Netherlands. And the small cells here are the Dutch Harmony model with 2.5 kilometers. And this is the same resolution we use in Austria right now. So, yeah, so we have now our weather forecast model, which provides us with forecasts for the next 10 days, roughly. And what do we do with it? So we use the weather forecast. And what I show you here is the ECMWF forecast for a date in 2022. And this is for wind speed at 135 meters above ground. So a typical hub height of wind turbines. And what you can see already is, if you're familiar with the Alpine range, you have in the west of Austria, you have the Inn Valley and Tyrol, Vorarlberg, and Switzerland right here, also South Tyrol. And what you see is there are no valleys. So there's not really an Alpine range present, even with 9 times 9 kilometers. What we see as well, the bigger valleys and plains in the eastern part of Austria, but we don't see valleys. And so with the red box would indicate a region in Austria which is used for wind energy. And if I use a point, this point representing my wind farm, and compare the wind speed to the observations at the turbine hub height, so the SCADA data, you see that at least for the eastern part of Austria, it works quite okayish. So in black, you see the observations, and in magenta, you see what the model would give you. But still, we do miss some wind speed maxima. We do miss some of the lower wind speeds. And in general, it is a bit smooth compared to the observations. So what does it mean in general? We cannot resolve every process explicitly with a global model. Even with a local model with 2.5 kilometers, it's hard to see small-scale processes. The system is very chaotic, and some processes are not well understood. And the components are connected also in a non-trivial way. So how the interaction of temperature with surface moisture, temperature, wind speed is non-trivial. And we have a huge number of observations to deal with, and even more when we're moving to the climate periods. And yeah. Now the question is, where can we use machine learning, or does machine learning help here? Yes, it does. It actually is even used. If we go to the observations, machine learning is heavily used in data monitoring and quality control to detect anomalies in the data sets, data cleaning and filtering for the longer historic time series, which we need, but also for spatial interpolation of data, data fusion, decision making, and correction of the errors. And right now, it's one interesting field is moving away from these typical interpolation methods like kriging or kriging with drift, and going into deep learning. So using observations, using different fields of topography, and using deep learning and the residuals to generate a map as like on a different horizontal resolutions. But machine learning is also used in the governing equations to, let's say, replace parameterizations, because parameterizations take a lot of time to calculate. And if you can emulate them with machine learning, it really changes the runtime of a typical weather forecasting models, which is in the range of at least 3 to 4 hours for the local models and 7 to 8 hours for global models. You can also perform bias correction for observations and other parameters, and you can perturb the data to generate an ensemble or merge different kinds of data. Yeah. What we also use it for, and this is done quite heavily, is in adjusting the forecasting products for renewable energy applications, for agriculture, for tourism, transportation and logistics, and also to improve the typical forecast products for subseasonal to seasonal prediction. So subseasonal to seasonal prediction is the range of 14 days to 3 to 4 months ahead. And as you might guess, with the chaotic nature of weather, this is non-trivial and typically smoothes into the climatology at a certain point in time. And there was a challenge last year of DCMWF, the S2S challenge, to improve the forecast products for subseasonal prediction using deep learning and other machine learning methods. It also helps us in feature detection. So we have, from those weather forecasting models, we get tons of data. We do not only get surface parameters of temperature and wind, humidity, we also get vertical components. We also get different types of data for the moisture fluxes, for the radiation fluxes, subsurface temperatures and moisture. So you have a lot of data. Typically, we meteorologists let us guide by knowledge. So when generating a post-processing model for, let's say, temperature, we say, yeah, well, temperature has an influence, wind speed has an influence, the pressure has an influence, and also precipitation, and maybe radiation. But there are other parameters available, and using feature detection and feature selection might reveal some interesting connections which you were not aware of in the first moment. So it really helps us improving the forecasts. And for uncertainty quantification, it's a cheap method to generate ensembles. So in weather forecasting at ECMWF, we have an ensemble of 50 weather forecasts. So we have 50 forecasts for the next 10 days, plus the control run. And as you might guess, this takes a lot of computation. And if there's a way of reducing this computational load by using machine learning models, which are able to provide a nice spread and mean for forecasting, this helps us already a lot. And also in kind of new field emerging is the purely data-driven forecasting, which is based on analysis. But it's also used for generation of synthetic data and data augmentation for algorithm training, and also for downscaling of climate models and weather forecasting models to sub-kilometer scale and also to sub-hourly. So to avoid for sub-hourly the typical linear interpolation between 2 points in time, which might work for temperature, but not so good for other parameters like wind. So post-processing, why it is important anyway. And as you've seen in the slides before, 9 times 9 kilometer is not really helpful, especially if you're in a region with complex terrain. And what you see here is a reanalysis product of the American NCAR Center called NERA2. And well, you do see from the topography here that there are some mountains or hills, but you wouldn't guess that this is the Alpine range. Moving to the ERA5 product, which has 25 times 25 kilometers, you see at least the Alpine range, but still it is, well, you would see Mont Blanc, you see Ortler range, but which is here, but you wouldn't guess that we have mountains more than 3,000 meters here. When you're moving to higher resolution of 6 kilometers, you already see quite nicely that there is something like mountains and valleys. But still, you don't see the small valleys here. You see the Brenner Valley, you see the Inn Valley. But that we have valleys here and here or here with Zillertal and other valleys, you don't really see. For the eastern part of Austria, it doesn't matter that much, but for the western part, it does matter. And if you compare it for a small subdomain in Austria, so this here would be the region with most of our wind energy sites, and some are also here in the mountainous areas. This is now for temperature. Well, you do not really see that there could be mountains. And for comparison, this is the same point in time of our own analysis fields with 1 times 1 kilometer. And what we do see that the model, the ECMWF, got temperatures right here and here. But for the rest, we don't really see that it's somehow reproducing the climate we have here. So we need post-processing. And you might say 1 kilometer values should be okay. Somehow, no. This is now our operational models with 2.5 kilometers, and dots are different wind farms in the eastern part of Austria. And the nice pink boxes represent one grid point. And you see already here that one wind farm would somehow fit into one box. So yes, you could use one box for the whole wind farm, but what you don't get or what you don't see are wakes of the turbines. So let's say if we have northwesterly wind direction and the wind approaches this wind farm, so this turbine would get the full amount of wind and would be able to produce quite a lot of wind energy. The wind farms behind, turbines behind it have already a reduced energy production due to the wakes of the first turbines. So to be able to really model or forecast for every turbine separately, we need to use post-processing. And also the numerical weather prediction models are prone to different kinds of errors, which are in data sources, in the assimilation, in the parameterizations. So, and often they are undispersive, and so we need to correct the spread and the bias of the model. And often TSOs and wind farm operators want to have a temporal resolution of sub-hourly. So let's say every 10 minutes per forecast, they want to know every 10 minutes what the production will be, or every 5 minutes. Sometimes you want to have it even in the 1 minute scale. And this is something you cannot do with a numerical weather prediction model. This is just too costly and also takes too much time. So we use post-processing, and it started all more than 50 years ago. End of the 50s, beginning of the 60s, with some classical methods. And they are based on the current observations and or, depending on what you have, the recent weather conditions, and have no numerical models. So you could consider the classical models already as sort of data-driven. You have the initial predictor, which is the observations, and the predictants, which are the weather conditions for training such a model. So you put this, the temperature for tomorrow, you calculate using the observation data set available at the time of the forecast. Or let's say I'm issuing a forecast right now. So every data I have up to right now of the past 24 hours, I'm going to use and put into my function. This works quite okay for the short ranges and for the very long ranges. So for the persistence and also for the climatological period. But for the medium range, this method has no skill at all. So yeah, doesn't really work. And it works best under persistent weather conditions, which would in Austria be a high pressure system in summer with sunshine and hardly any wind. The next method, which is often referred to, is the perfect prognosis approach. So they noticed that this is not really working with the classical approach. So we're going to use the perfect prognosis approach.
Irene, there's one question.
Yeah.
Yeah. Kioli, could you please ask directly?
Yes. So can you hear me?
Yes.
Yeah. Okay. Could you maybe to the previous slides? Yeah. So I have questions in this part actually. So this functions one is that there is the sum. So it's actually the the predictions that at time t. So it depends on the previous or the previous of the time, or actually it's only that the initial time at 0. So I'm a little bit confused in this part.
It depends. It really depends. You need to look into the autocorrelation of the parameter and decide how many previous time steps you use.
So my question is that this part x is only x0 or actually is, for example, is x0 to x t minus 1. I'm not so clear about this part.
This part really depends on what you have available and what you want to put into. So it can be either the time, the value which you have right now, or the past values of, let's say, the last 2 hours or last 2
Is
days.
it possible that there was some problem with the rendering of the equation? It seems that there's a bit missing in equation 1, or what are these dots standing for?
The dots are standing for nothing really. They're just a space for leading to 1.
And this summation is over which variable, or what is the summation index?
Over time.
Time.
Yeah.
Okay, then maybe it's for time. Okay, then
It's for time, yeah.
Yeah, okay, then it might be for time from 0 to time t. So, and yeah, and another question that, for example, this predicted at time t. So does this predict at time t depend on the predictions of the y, for example, y 0 or something like that? Or it's only dependent on x?
It's dependent on x and a function you decide on. So there are, it really depends on the parameter. It depends on the data you have available. So there is no general equation for this classical method.
Yeah, okay, thanks.
What you could also consider as classical method is the persistence, where you just fill the forecast vector with the most recent observation.
Yeah.
Without any function.
Yeah, okay.
So there is no real best guidance on this classical method.
Yeah, but I just think that the function should be a little bit general. For example, maybe the parameters could be there, but the function should be a little bit general. I'm just thinking that.
Mm-hmm.
Yeah. Okay.
Yeah. And the perfect prognosis approach is based on the assumption that a numerical weather prediction model forecast is always perfect, which they aren't, but still sometimes it works. And what you have is you have a predictor, which is your observation, or a numerical weather prediction model at some point, and you have the predictance. So you have observations and observations of historical ones or climate data. Then you put it into your relationship equation. You add the model forecast, and then you have the perfect prognosis. But you have to make sure that the parameters you use as predictor are available from the numerical weather prediction model. And this perfect prognosis approach is very similar to an analog approach. So in the perfect prognosis approach, you have observations and compare to observations, and then you add the numerical weather prediction model for the forecast, assuming that this numerical weather prediction data is your predictor. And in the analog method, this one actually also dates back quite a while and has been sort of rediscovered in the early 2010 years, where you compare the current state of the atmosphere with a repository of other historical states of the atmosphere. And then you calculate the distance between those, between the actual date and the repo, and select the most similar scenarios or dates in the past. And so you have a forecast which needs to be corrected at time t and at a specific location. And you have your analog forecast at time t, which is sometime before our recent forecast. issued, but for the same location. And then you have the number of predictors and the weights. So if I'm trying to make a prediction for temperature, then I would have temperature, previous temperature, let's say wind speed, precipitation. And this would sum up to 5 predictors and the weights you assign to them. Then you have the standard deviation of the time series of the past forecasts for the variable at the same location. And then you calculate the values or the difference of values of prediction and the analog in the time window. And based on this metric, you choose your best fitting analogs of the past and generate a new forecast. And you can either choose the strategy of, if I have a forecast for, let's say, 12 UTC, then I only look for past dates at 12 UTC. But you can also make a sliding window approach of ±3 hours. And this depends really on what actually produces the best results. And this you carry out for a forecast of the next 48 hours. The method has some advantages because it don't really need a lot of data, but it's slow because I have to load the repository every time I issue a forecast. I have to load my repository of past dates and perform my search, and this can be really, really slow. For single points, it's quite okay, but if I'm moving to a grid and try to do the same for a grid, then it really takes a lot of time. And there exist already some sort of hybrid methods which combine the neural networks and the analogs method. So where you define the weights using a neural network and other things. And one example would be the CAPSNet method, which is used for extreme events prediction. And another analog method which we implemented recently is a method which also considers not only my past recordings at the same point I'm forecasting, but takes a spatial field surrounding my point of interest into account. So I would not only use data at the red dots here, but I would use data in a certain surrounding depending on my season, for instance. And this we implemented right now for nowcasting. And this would be a purely data-driven approach where no numerical weather prediction model is included right now. And we do this to forecast solar energy production based on satellite data of the meteor generation. And this we managed to make the code managed to run quite fast as the student had some troubles with his RAM on his laptop. So he had to fit everything into, I think, 4 GB RAM. And it was really heavily transformed into a really good working algorithm. And this would be the k-nearest neighbor analogs search algorithm, which is performed already on the compressed images. So we use here right now a nearest neighbor approach. And this could be also exchanged in the future with another maybe better performing approach for the analog search. And for post-processing, there exist tons of other methods, and I will not show them here right now because this would be too much, but one would be model output statistics, where you have the bias of the numerical weather prediction model of the past forecasts and use this bias to adjust the current forecast. Bayesian model averaging and ECC and Schicker shuffle would also be post-processing methods. And we have currently running a hybrid method, which is called ensemble model output statistics. And it's hybrid because we use already boosting of the parameters. And originally it was implemented in Fortran and it was rewritten to R and Python. And this would be the old Fortran code where we use the Melder-Mead minimization algorithm to find the local minimum. And this is an example of how a spatial forecast would look like. And this wind farm is one of the wind farms I showed you before. So we see here already the post-processed forecast, and here for the wind farm, we see already how the wind field is in this wind farm. So we see that we have turbines with more wind speed and turbines with not so much wind speed like this one here. And this is the turbine below, and this is the turbine here on top. And in black is the observation. So we also see we have some gaps in the observations. And in green would be this boosted statistics, and in red would be the raw model forecast. And the same was transformed into using anomalies to be able to fit not only at points where we have observations, but also at other points. So some sort of, or you could call it, I think, transfer learning, but in a very, very basic way. And this works quite well, as we can see in this example. And it's based on the assumption that we use the climatology for every point, subtract the recent forecast and observations from the climatology. So we are left with these residuals and fit the algorithm only to the residuals. So we have the seasonal effect and the altitude effect excluded already. And I will try to speed up a bit. And what we use right now are different kinds of machine learning models for different applications, mainly for renewables, but also for agricultural applications and transportation, logistics, and also for road maintenance. So predicting the pavement temperatures for especially for winter conditions and road maintenance. And we have the different kinds of observations, and like the PWS, which are the private weather stations, like NetAtmo, and also microlink data between the mobile masts, and also mobile devices are often looked into right now. And we use different kinds of machine learning methods. What we have right now are the classical ones, like the feed-forward neural network, which we use as an ensemble of network, and then use the ensemble mean as a forecast. And we also have a random forest version of this forecast for wind energy production. And what you can see in this example is that the neural network performed quite well compared to the observations. And also the random forest performed quite okay-ish. And in green would be the raw model forecast. The advantage is that we have direct access to online data of the turbines. And we have quite a lot of data for training. So for some turbines, we have now 5 years of data for training, which is quite a lot in wind energy. Often you're lucky if you get a year of data for training, sometimes even less than a year. What we also use is convolutional LSTMs and classical and convolutional neural networks, but also sequence-to-sequence networks. And I'm going to jump over this, and this would be an example of providing spatial predictions, where we use our high-resolution observation-based analysis and perform high-resolution forecasts of different parameters, and have some sort of two-branch model where we feed in the observations and feed in the model and combine these two. And we have the classical neural network to be able to compare to a classical method, but also a CNN. And this is how the code for the model looks like. So there's nothing too fancy, nothing too deep, because we are also taking into account model changes of the NWP model, where you have version updates every half a year or every year. And we're also going to replace the core in the next step using a convolutional LSTM with adapted weights in the loss function and also adapted metrics. And this is what the convolutional neural network, the LSTM, provides us with for wind speed category forecasts. And this would be for a forecast of wind speed extremes exceeding, I think it's here 18 meters per second. And so we have the input to the new convolutional LSTM. This would be our target, and this is what we get from our convolutional LSTM. And these are different time steps into the future. And we see here that for the first hours, it's a bit overshooting and a bit too much in some regions. But here for the latest time point, it's quite good compared to the observed. And it's data-driven. It uses only reanalysis data as input. And here we use 10 years of input. But in principle, you would have 40 years of era 5 data going back to 1979. And I think they even extended it to the 1950s. But I'm not sure how much of the data is available right now. And the loss function here was adapted with a weighting to the less frequent cases of wind speed. So especially for the extremes, because there are not so many cases of more than 18 meters per second. And also the metrics function was adapted. And this is how the code looks like. So there's also not part of the code. There's also not too much fancy stuff in there, but it works quite well. And we also do the same, something similar for solar energy forecasting, where we use different kind of input at observation sites for 3 sites in the eastern part of Austria. And we have 15-minute forecast for the next 6 hours ahead. And we have here sequence-to-sequence neural network. And we have artificial data using this PVLib, because we only have 1 year of observation data of the power plants. And we had a look into how good this performs, and it performs quite okay. And I'm going to skip this, and here are some of the results. So what we see is that the LSTM most of the time performs quite well, especially in this adjusted version where we train separate models for every lead time ahead. And now to the probably more interesting part for all of you. So recently, graph neural networks are being used in meteorology, and especially with focus on wind and solar energy prediction. And there are 2 examples. So above you see for wind energy prediction, and in the lower one you see for solar energy prediction in the United States. And with a range of forecasts, so sort of ensemble forecast. And these performed quite well because you are able to include a lot of data in the surroundings, and this makes sense. So if you have a cloud moving from the west to the east, you know ahead in time for the eastern part what will happen and can adapt accordingly. And fields of application for federated learning, also graph neural networks and different kinds of graph networks are really useful in renewable energy. In renewable energy, typically, you don't get a lot of data from the providers. So you're lucky if you get a year of data, but sometimes you don't even get observation data because of the policies. So if you're in a project with different wind energy providers, for instance, you have an NDA. So you're lucky if you can use the data all together in one model. But sometimes you're not even allowed to mix the data storage. So you have to come up with an idea on how to train your model or how to improve your model. And here federated learning, especially network federated learning, could help a lot because you can transfer the model just to the TSOs or wherever they have their models running and train it on their data. You don't have a problem with data policies, and it would definitely help to improve forecasts if you have different providers overall of Europe. It would really help improving the forecast, and it would also help improving meteorological forecast because you could combine different sources. You could also combine, let's say, Austrian observations with France, the Netherlands, without actually having to transfer the data to your location. So what we do right now is we do transfer the data to our own data center. And this would be very easier if you don't have to transfer the data and just train every model separately. And you could also combine it even with private weather observation sites after the quality control of the sites. And you can also provide forecasts for mobility applications like car measurements, or providing a driver with the forecast ahead of his location, or even using his data to train a model in his car, let's say. So there are different applications you could use federated learning in meteorology, but so far it's still in its infancy. So there are not real big applications right now. But I think especially with renewable energy, this would be really the next step to improve locations at a point. Yeah. And I will skip this slide. And if you have any questions or recommendations, comments, I'm open for it.
Thanks a lot, Irene, for this excellent overview of machine learning problems and applications and methods in meteorology. Please, anybody with questions, come forward. So then I will go forward with my questions. One very hot topic is the transition to more renewable energies. So could you maybe give a few key challenges, or what are the key requirements when it comes to weather forecasting for operating a solar panel, so photovoltaics and wind energy? Kind of what is the typical time horizon you need to have a good forecast, and what are the the requirements for the precision. So do I need to get an accuracy of up to 1 meter per second wind speed accuracy? What is the requirement for the precision of predicting the amount of sunshine per day? So do you have a few numbers on this?
So for wind energy, you can say roughly that 1 meter, that the wind speed and the power generated by the wind speed is the cubic.
Mm-hmm.
So you have to take the cubic and then rotor diameter. But so every error in the forecasted wind speed is tripled,
Mm-hmm.
at least
Mm-hmm.
tripled. So here you have to be really, really super accurate.
Mm-hmm.
For solar energy, it's a bit different because solar energy is really, really highly fluctuant. Right now, or the last days, we had the Saharan dust again in Central Europe, and so depending on how much aerosols you have in the atmosphere, how often you have clouds passing the kind of window of sight of one solar panel, you have different amount of energy produced. And also it depends on the temperature. If it's too hot, you cannot produce a lot. If it's hot and windy, it's a bit better again. So you have here some really the need for high accuracy and the need for high frequency forecasts. The time window you have to provide the forecast, or which is important for the TSOs, varies. So you have the intraday, which is very important because they really have to adjust pretty fast, especially in summer with all the thunderstorm events. But for the day ahead or the days ahead, yes, they want to have high accuracy and sub-hourly and everything, but you can adapt on the day. So if I produce a forecast for tomorrow and I'm off by, let's say, a couple of megawatts, it's not nice, but they still can adapt the forecast and take prevention measures. So intraday is really, really super important that you're as accurate as possible. Day ahead, a bit less.
Okay, thanks a lot. So then here's one question related to graph neural networks. So as I understood, currently you use graph neural networks in a standard machine learning training mode. So you collect all data and train a graph neural network. So where do you see how this could be combined with a distributed federated approach, where you have like one graph neural network in France, one graph neural network in Austria? So you would then basically share only the weights of the graph neural networks between each other instead of the raw data.
Exactly. So I would share the weights and adjust the model, but I would not need the data in-house.
Yeah.
And this is especially important especially for the renewable energy sector, because they don't like to share data.
There's this, so the typical approach in computer vision, as I understood, to use transfer learning with deep neural networks is you look out for an open repository of somebody who did a project on similar data. Like I want to develop an object detector or a person detector from a drone video. So what do? I Google for GitHub repositories, drone video object detection. And typically these Git repositories have the trained model parameters. Is there something similar in the field of meteorology? So you have a pre-trained model for Austrian solar energy forecasting, you have a model for France, and so on and so forth?
Yes and no. It also depends on the policy. So in Austria, in our institutions right now, there are, as far as I know, hardly any open repositories. It also depends on where the project was funded. Swiss Met Office, FMI, the Belgian Met Office, and I think also the Dutch Met Office, they do share quite a lot of things. also the Norwegian Met Office, but not everything.
Mhm.
And there are also open resources published in papers. And the graph network I showed you before, let's go back to the slide. This one here. So this one here, the graph network for wind and solar was used for wind energy prediction in Denmark and in the Netherlands. And this is available on GitHub. The full code and even the Dutch data are available. And I did not check, but I think also the weights are available. But you can also train it yourself, the model. So for this, everything is available. There are also downscaling codes using deep learning, which are available. And also the code for this work here, where you interpolate the observations into a spatial field of 1 kilometer or even higher resolution, is available on GitHub. So there is no clear answer to that. It really depends. France Met Office has I think not a lot open, similar to us.
So there's one related question, but I don't quite understand this question. So how can you guarantee that the graph neural network in different locations are the same for the parameter updates? I guess everybody trains his or her own graph neural network. So nobody guarantees that they are the same. There is no authority, or which could be the authority to oversee such transfer learning. Is there some European, or is it this European Meteorological Institute?
No, not really. So the ECMWF can provide guidelines, and also the WMO could provide guidelines or best practices, but there is no one overseeing it.
Yeah.
So it's more like a hand-in-hand coordination like thing between researchers.
Yeah. Okay. Then another question, maybe the last question I would like to forward: how the graph neural network is used in non-federated models, since not necessarily the sites are correlated. So the kind of more specification. I mean that there are edges what are the edges of the graph neural network representing? Yeah, here below in the bottom line, the middle graph, what are the edges here?
These are the measurements of the solar radiation database, and should be the parameter global horizontal irradiance. But I would need to check in detail in the paper again. Yes,
but I assume these links or edges in this graph, they represent correlations between the nodes.
I think they represent the correlations between, and
how are these measured? How are these correlations estimated somehow, data driven, or based on some modeling? Like this location and this location, they are both in a valley, so they have a high correlation.
These are data driven, and looking at the image, which is close to, so the data is close to Chicago. So I would say the red ones are the ones located in the vicinity of Chicago and densely urban or rural area. Whereas the orange ones share other similarities, like being somehow in the flat. And for Austria, I would say, so if I would relate this to Austria, then I would say something like the ones sharing similar valley characteristics would be connected. Yeah.
So there goes into a lot of domain expertise, I assume. I mean, what you can do naively or intuitively, you look at the locations and connect two if they are close by within 10 kilometers. That's what we also do in our exercises, actually. We have a toy there's nice description of programming interface for the Finnish Meteorological Institute, where you can scrape all observations within a rectangular region, and you get the observations with timestamp and with the name of the weather station. Then we say we have at each weather station we have a data set, all the measurements there, and we connect two if they are close to each other in the distance. But then I assume you might bring in more knowledge into this network structure by looking at the precise topography. And as I understood, during your talk, you talked about such initiatives using where this deep learning approaches, they take into account the geographic locations and the specific properties of the landscape.
So there are different approaches. One approach would be really like data-driven, but not distance-wise. But like I have here in this picture, unfortunately, I did not add the clustering results. So we developed a clustering algorithm based on wavelets, where you only feed in the measurements of the observation sites at the time series. And then the cluster algorithm finds similar clusters, observation sites with similar clusters. So no distance measurements so just the data, and then you find similarities.
But instead of the distance between two measurement stations, you calculate, as I understand, a similarity in the statistical properties or patterns in this measurement.
Exactly.
Using wavelets.
Using the wavelets, wavelet trees. And unfortunately, the paper, we have to rewrite it again. But the student first applied it to our Austrian observation sites. And using the data, she could show that the algorithm works in a way that her results represented the classical Köppen-Geiger climate, how are they called? Climate fields in Austria. So like the typical Pannonian climate and everything.
The clustering made sense. You were able to validate the clustering.
Exactly. So you were able to validate the clustering. You could also see that the clusters along the Danube or the sites along the Danube nicely correlated. And we did something similar for the wind parks. So
that's actually perfect now that we have this. So sorry for now being a bit pushy and wrapping up, but this is now an excellent bridge to our next lecture in a bit less than 1 hour at 1, where we hear about clustered federated learning. And there the problem is exactly how to find out if two data sets, like on two different weather stations, belong to the same cluster. And you will then hear about such methods more in the next lectures. But let me thank you again, Irene. It was an excellent and interesting lecture. I would like then to share the recording with the participants, if this is okay with you.
Yeah, fine for me.
And if you could forward me your slides, I will also share it in whenever you can. Okay.
I will. Okay. Thank you very much.
Thanks a lot again.
Thank you.
Ciao.
Bye.